Okay. Our next speaker is Max Wiesner. He will tell us about minimal volumes in string compactifications.
Thanks a lot, Jose, and of course, thanks a lot to the organizers for putting together this wonderful conference in this wonderful city. Makes me want to come back. And I want to talk about some work I did with actually a subset of the organizers, Cesar, Alessandro, and Timo, who are sitting in that corner, and some work in progress, which deals roughly with minimal volumes and string compactifications. And I mean, this is a geometry and strings conference, and I mean, we know that geometric compactification of string theory gives us a wide range of consistent theories of quantum gravity. It's an interesting playground to test what we know about gravity in lower dimensions, for example, string theory, M theory, F theory on some manifold X. But of course, the geometric description typically requires that we have some kind of large volume, so we want to have all submanifolds of this manifold X to be large compared to the fundamental gravity scale, which I just call lambda quantum gravity, which can be, of course, the 11D M theory scale, the strings theory scale, you name it. But of course, the question is what happens if we leave this regime? Normally, we would expect that, of course, the original EFT breaks down because the KK scale becomes way bigger than the quantum gravity cutoff. New degrees of freedom become important, or quantum corrections can appear. On the other hand, of course, we expect that the full theory of quantum gravity knows how to deal with this limit. It's just, of course, if we go to one duality limit or one large volume regime, it has a particularly simple description, but it knows how to deal with the small volume regimes. And this, of course, we also know in the simplest example how it does that, either via T-duality, because we know that the small volume regime of one string theory is just a large volume regime of another one, or of course M theory on a circle just gives us a genuine 10-dimensional theory, which is of course just type 2A string theory. Then if we go further down, for example, we know that if we have small shrinkable cycles and we get massless charged states, so we just need to augment our theory with some additional charged states, but still the geometric description is still valid, which is typically thanks to enhanced supersymmetry. Or, of course, there can be quantum corrections, for example, in type 2A string theory compactifications of Calabi-Yau three-folds, worldsheet instantons, and one can see that the overall quantum volume of the Calabi-Yau never vanishes. But, of course, an important question is what happens in theories with minimal supersymmetry, where oftentimes we do not have like the circuit along which we can T-dualize. We not necessarily have non-renormalization theorems that tell us that we can trust geometry all the way to the real small volume limit. So why do we care? Of course, because the small volume limit is somehow where the quantum gravity effects really become relevant. That's where we see duality frames, where we see additional light states that we actually need to include, and we see real effects of quantum gravity. And of course, we can view it as some opposite regime of the large volume or the supergravity regime, so we can really see this is the difference if we would just do supergravity versus the full quantum gravity. And another motivation is because some refinements of Swampland constraints are motivated by dimensional reduction. For example, the tower weak gravity conjecture, which states that if we take a d-dimensional theory of gravity with some U1 gauge symmetry, then we know that the weak gravity conjecture requires a super extremal charge state. And now in this series of papers, they ask, okay, what happens when we circle compactify this to a d-1 dimensional theory and we have an additional KK-U1? The weak gravity conjecture in the d-1 dimensional theory then actually gets enhanced to a convex Hull condition for this original U1D and the KK-U1. And now the observation in these papers is if we now actually take the small radius limit, we require a tower of super extremal states in the capital D-dimensional theory to actually satisfy the convex Hull condition. So this is another kind of motivation why we should look at the small radius limit, and which was actually the motivation to look in this paper with the Hamburg crew later last year. Because the caveat, of course, for this tower weak gravity conjecture logic that was already pointed out in these original papers is if there actually exists a minimal radius beyond which we cannot view the theory as a d-dimensional theory compactified on a circle. And so we looked at this again in theories with minimal supersymmetry. So we took, for example, F theory on T2, an elliptic vibration over B2, so 6D n equal to 1, or M theory on Calabi-Yau 3, 5D n equal to 1, with non-trivial abelian gauge factor, which gives us the higher dimensional gauge factor in the theory, and we ask what happens under further compactification on an S1, and where we considered what happens if we actually go to the regime where this radius becomes of order of the quantum gravity cutoff, which can be which can be the 2b or the M11 case. And the question was, is there a minimal radius beyond which I cannot view this theory as a circle compactification of a higher dimension theory, therefore providing this caveat? In this talk, because this is strings and geometry and not Swamplandia, I want to focus on the geometric part of the analysis. And for the people who go next week to Seon, to the Abbey, I refer to Alessandro's talk, who will more talk about the Swampland aspects of this this analysis. So starting with the F theory regime, so we take 60 n equal to 1 obtained from an F theory on an elliptically fibered Calabi-Yau threefold. And of course, I realized, or I reviewed before, how typically string theory deals with small volumes, either by duality, which requires us a two-form coupling to some critical string, or either we have this M type 2A duality, where we actually have a genuine d-1 dimensional theory, which we do not have both in this case, is because we do not have the critical string in the F theory because it gets projected out, and in particular, we do not have the two-form. Additional states is also not really, because the circle that I want to look at or the curve, the cycle I want to look at is just the circle. So so we actually have that naively in this limit, the KK tower becomes very strongly very heavy. So it's not just a shrinkable cycle that we shrink and expect additional states. And then one might ask what about quantum effects, where one would naively think, okay, instanton effects, all of these kinds should be absent because we're still in too high dimensions if we look at the tensor branch. So what is happening in this case? Let us therefore look at the basic dictionary between F and M theory, which tells us that if we are interested in F theory on a base B2 times a circle, this is of course dual to M theory on the elliptic fibration over B2, where we identify the radius with the inverse volume of the M theory torus. And so the usual F theory limit is just we take the tau to 0 limit while making the weights large, which just tells us that this radius goes to infinity. Of course, here we're interested in the opposite limit, where we want to make the radius very small, meaning that we want to take tau much larger than 1. And the question is, can we still view this theory as a 60 theory on an S1? One criterion for this could be, or that we observed, because it's true in the T dualities or in the 1011D duality frame, is that actually the KK tower should be lighter than the black hole threshold in the theory, so the smallest black hole, which can be higher dimensional in the theory. And to actually answer this question, we consider the M theory dual description, because that's the easiest there, where we have all the magic of geometry. So the question is, consider this limit, and do we actually get a 60 theory on a circle? So the F theory circle manifests, of course, in the vibration structure of the Calabi-Yau. So we have a T2 over B2, and if we now go into the actual F theory limit, we have this factorized volume, tau times the volume of B2. But if the vibration is non-trivial, we get corrections that are proportional to tau squared and tau cubed in the volume, which dominate, of course, in the regime that we're interested in, where tau is much bigger than 1, unless, of course, the coefficients of this guy vanish. But this already tells us that if in the generic case where these are non-vanishing, we get, if we make tau much larger than 1, we cannot help but going also to very large volume for the X3, which means that actually we're now moving in the hypermultiplet moduli space, which initially we didn't want because we wanted to keep the volume of X3 fixed. So it would be a decompactification actually to full 11DM theory. So we effectively have here a minimal radius, which is given by the maximal volume for tau, such that actually this is the volume here of the full volume of X3 is 1, so we want to have the maximal tau that this condition is satisfied. And the interpretation is that we can only view this as an F theory or like a 6-die theory on B2 times S1 if there's actually a hierarchy of scales, meaning that the typical length scale of this B2 is much smaller than the length scale of the S1. Or, from the F theory perspective, actually these corrections here can be interpreted as coming from webbed F1 D1 strings that induce the minimal radius, which is then captured by the full geometry in M theory. So to some extent, you can view these extra corrections that we do not have in the F theory limit as corrections that are captured by the M theory from the F theory perspective. Of course, one can now ask what happens if alpha and beta is 0. And that one can consider a simple example where we have an elliptic vibration over P2 with an extra section. So we have a U1 gauge theory in 6D, H11 is 3, so we can expand the Kähler form just like this. So we have the shifted zero section of the vibration, we have the extra section, or the Shioda map associated to this extra U1, and we have a vertical divisor coming just from the vibration over the hyperplane class in P2. So we can now define a Coulomb branch parameter, which is basically the ratio between Z and tau. And we can write the overall volume of the X3 in this unit in terms of tau and theta. And one can see very quickly that alpha and beta, so the coefficients of the tau cubed and the tau squared term, vanish if theta is equal to 1/2. So one may ask, okay, is actually tau max going to infinity if we tune our Coulomb branch parameter accordingly? The answer here is again no, because in this limit, X3 is best viewed as a one-parameter K3 vibration over P1. So this is what we started with. This was the elliptic vibration over P2. But if we now make this curve C1, which is actually a fibril curve here, very large, which corresponds to the limit where we actually make tau very large and going to theta equal to 1/2, it's better viewed as a K3 vibration over C1, which is incompatible with the original elliptic vibration. And here we get a weakly coupled heterotic string. Its tension sets the quantum gravity cutoff for large tau. But this dual heterotic string is compactified on K3 times S1, where the S1 is now fixed at the self-dual radius. So again, we cannot actually do not get a theory where we make this, the radius arbitrarily small. So even if tau is is possible, we still have a radius which is here set by the duality frame. So the upshot is that in F-theory on B2 times S1, we always have a minimal radius for the S1, which is either induced by the quantum corrections as captured by the full M-theory geometry, which is the generic case, or the duality to the heterotic string at fixed radius. So we always have a minimal radius in this F-theory compactifications on an additional S1. One can then go further down and say, okay, now let's do an extra circle compactification, M-theory on Calabi 3 times S1. And so we can view this, of course, as F3 on B2 times C2. So we have a minimal radius for one S1. So the natural expectation is that we also get generically a minimal radius for the second S1. Of course, here it's easier to work directly in M theory on Calabi 3 times S1. So I'm not going through F theory. So starting here with M theory just on X3. So in 5D, we have this relation between the volume of X in M theory units and the Planck scale. And we want to further compactify on an S1 while keeping the overall volume fixed. And the question is, can we take actually the limit where we make this S1 small while keeping the volume in M-theory unit fixed? Looking at our M-theory type 2A duality, which of course identifies the 2A string coupling with the radius in M-theory units, we see that of course, that we all know is that the overall volume in M-theory units is a universal hypermultiplet. And so keeping this fixed, we really just move in the vector multiplet case, and we don't touch the universal hypermultiplet. So now the small radius limit, if we just plug in this relation, tells us, okay, we want this to go to 0, so this ratio also needs to go to 0. Since we want to keep this fixed, this requires, of course, to take the volume of the Calabi in string units, which is this S to 0. Of course, in this regime, we know that the alpha prime corrections become important. And one can actually show that this limit is not part of the quantum modular space. How do we see this? We look at what is actually the quantum volume of this Calabi, which can be computed by a mirror symmetry, because it's just you can look at the Kähler potential, e to the Kähler potential in the mirror. And so this is actually bounded, as one can see in examples, by an order 1 parameter. And this sets the minimal radius. So example quintic, it was here before, but now it's gone. We see that the minimal radius is obtained at the Landau-Ginzburg point, where it actually takes some numerical order 1 value, which of course also corresponds to the desert point in the complex structure modular space of the mirror quintic, which is what we observed here. And so we get a minimal radius depending on the value we choose in the hypermultiplet, and depending on the third root of this number. And again, note that the Wilson line modulus of the 5D gauge theory, 5D U1 that we had, is again tuned to 1/2 at the Landau-Ginzburg point, at this point phi equal to 0, which is actually what we also observed in the compactification from 6D to 5D. So there exists a minimal radius, And beyond this value, the interpretation of a 5D theory on a circle breaks down because, for example, the KK radius, the KK scale is much larger than the black hole scale. But this is, of course, not a bound on G2A. We can still make the string coupling arbitrarily small. It's just that this is a limit in the hypermultiplet sector, and not originally as one would have expected if we have a circle compactification in the vector multiplet sector. And this is, again, the consequence of the quantum geometry of the compactification, because the description of the circle requires here the hierarchy now that the circle is much larger than the typical length scale in the Calabi-Yau, because otherwise they mix precisely by these quantum corrections. But note that, of course, this does not occur in the circle compactification of just 11D M theory, because there we just do not have another length scale, so that we can actually take also this doesn't occur there. So we can then compare the 60-40, 5D-40 perspectives, and we observe that we in both cases get a minimal radius, once from the duality to M theory, which actually captures quantum corrections to F theory in classical terms due to non-trivial fibration. And once through the duality, we can see it to type 2A, because the quantum corrections are, of course, via mirror symmetry captured by the classical terms in the mirror. And the interpretation of the circle compactification always requires this kind of hierarchy, because otherwise the scales that we have in the compact space or in the original space are compared to the length scale of the circle. And if this is not satisfied, we actually the quantum corrections mix them all, and this interpretation of a circle compactification of a high-dimensional theory breaks down. And if we want to go beyond this, this necessarily pushes us into a limit in the hypermultiplet sector. Okay, and for implications of this minimal radius, I again refer to Alessandro's talk next week at Swampland. Now, of course, the question is, okay, this was 60 n equal to 1, 0, 5D n equal to 1. What about minimal volumes in 40 n equal to 1? So here one can, for example, now take F theory, not on a torus or Calabi-Yau 3 times D2, but actually on a genuine Calabi-Yau 4-fold, where we know that the scalar field space is spanned by the complex structure of the full 4-fold and the volumes of devices of B3. And in the large volume regime, we know, of course, all supersymmetry breaking effects are diluted, because basically the volume plays the role of the 4D dilaton. And when we have the simple like supergravity description in terms of the scalar potential. But the question is now, what happens away from the overall large volume limit? So in particular, are there minimal volumes for curves inside B3? And so if this theory was n equal to 2, so if this was actually type 2A compactified on Calabi-Yau 3, then we could look at the shrinkable curves, and we know that actually are shrinkable. For example, we can look at the flop curve. So here only a curve shrinks, and we can trust the geometric description of the Calabi-Yau of type 2A. It's just a flop transition. But so now what happens? The question is, what happens in the small volume limit for such a curve if this is actually inside the base B3 of an F theory geometry? So from the type 2A perspective, we would expect, okay, if we shrink this, there's a conifold singularity where the volume just vanishes. And since this curve actually in B3 does not intersect the anticanonical bundle, so locally C sees enhanced supersymmetry, which we can ask. So if we ask this question in the full F theory geometry, can we use this to our benefit? And so we look at the local geometry. We have the curve C. We want to flop it. And in the small volume limits for C, we should encounter locally enhanced supersymmetry, since, for example, a D3 brane wrapped on the C has enhanced supersymmetry. So this then looks actually locally like type 2B on a Calabi-Yau 3-fold, where the small volume limit should be locally described in the type 2B hypermultiplet sector, which is actually analog to local SUSY enhancement in F theory models with the base B2 is equal to F2. So classically, we would say, okay, the volume where the volume shrinks is a conifold singularity, but in the hypermultiplet sector, we know that we cannot have such conifold singularities because the hypermultiplet model space has constant curvature. We actually also know that the conifold singularity is resolved at the quantum level. So we would expect to have a description in terms of an n equal to 2 hypermultiplet associated to C, but so what are actually the additional fields that we need to make out of an n equal to 1 chiral field and n equal to 2 hypermultiplet, because the n equal to 1 effective theory only gives us 2 scalars, which is the volume and the dual of the C4 form period, because the periods of C2 and B2 over C, if we think about type 2b, are of course fixed to 0. So we need 2 additional scalar fields to complete the hypermultiplet, and this is actually obtained if we consider the factorization of the flop. So we say, okay, it splits into 2 curves, C prime, C double prime, such that we get a new fourfold that has delta H11 compared, or has 1 additional Kähler modulus, and the volumes of the curves are identified in this way. Or if we talk in terms of the string n equal to 2 string, it splits into 2 n equal to 1 strings living on this curve because they intersect the canonical bundle. So we have this situation. The theory on X4 should now be realized on a sublocus of the deformation space of X hat 4, which has, so this would be the local geometry of X4, this is the local geometry of X hat 4. And so this suggests, because we do not want to change the Euler characteristic, because then we would need to have additional flux, this suggests that also delta H2, 1 is 1, which from the type 2b perspective means actually that we get 2 additional axions from periods C2 and B2, which are counted by this H21. So these extra deformation then complete the would-be n equal to 2 hypermultiplet. And so one can now ask, how do we embed this original moduli space in X4? So it should be in general a non-singular locus. So both the strings that we wrap here and here should have finite tension. And so the expectation is just that we embed MX4 MX hat 4 at the loci where these actually take the minimal classical tangent for the D3 branes on C prime. And so the classical flop boundary now corresponds just to where these have the same volume. But importantly, we can now describe M-hex4 locally described by an n equal to 2 hypermultiplet space, where we don't expect a singularity because it should be resolved. And in particular, this means that the tension of this brane on C should be finite at the quantum level, which also means that the quantum volume of the curve C should be finite, which is hence very different from what we would have expected in the n equal to 2 theory. And let me actually skip over this in the interest of time and go to my conclusion. So the question was, in string compactifications with minimal supersymmetry, do we typically get minimal volumes? So the simplest case we consider for the circle compactifications of F and M theory and Calabi-Yau threefolds. And there we saw that quantum corrections generically induce minimal radius, below which we cannot view it as a circle reduction of a higher dimensional theory. There exists a duality frame in which the corrections are actually captured by the classical geometry, either by a duality to M theory on Calabi-Yau 3 or using mirror symmetry. And beyond the minimal radius, we are forced to move in the hypermultiplet modular space of the lower dimensional EFT. Also, I discussed for the n equal to 1 that there are in general also minimal radius for classically shrinkable curves, because the small volume limit is here also described by a hypermultiplet sector of a would-be n equal to 2 theory, where we see that we get a minimal quantum tension for a string wrapped on the shrinkable curve, which tells us that there's also a minimal volume for this curve beyond which we should not view it actually as a curve inside compact Calabi-Yau. So thank you very much.